Hello everyone, I am here to present our paper, ReinforceBug, a framework to generate adversarial textual examples. My name is Bushra Sabir and the co-authors of this work are Muhammad Ali Babar and Gaire. We are associated with Center of Research on Engineering Software Technologies, CREST, School of Computer Science, the University of Adelaide, Australia, and Skyros Data 61. So what are adversarial examples? Adversarial examples are a perturbed version of the original example on which the machine learning model tends to produce an incorrect output. For instance, consider this example, the fish and chips are excellent. Converting excellent to first class changes the output of the text classification model from positive to negative review. Hence, this determines that deep learning models are sensitive to adversarial examples, and when the models are subjected to such adversarial examples at test time, this is called an evasion attack. So why to generate adversarial examples? Including adversarial example as a part of training data can enhance the robustness and generalization of models as shown by prior works. These examples can be utilized to test the robustness of ML models and can help to understand security vulnerabilities and limitations of these models. So what motivated our research? Our research is motivated by the limitations of prior work. For example, the first limitations of prior work is utility preservation. By utility, we mean that adversarial examples generated by prior works do not fulfill the semantic, functional, and lexical equivalence with the original example. Consider the example generated by TextBugger's state-of-the-art attack to generate adversarial examples. This attack converts the original tweet that was spam to a benign tweet with a confidence of 68%. As it can be seen that the URL has been updated by the attack. The URL produced by the attack is an invalid URL, thus it violates the functional semantics. Moreover, the benign confidence is only 68%, which means the model has low prediction confidence on the new label. Similarly, another state-of-the-art model, TextFooler, converts the non-toxic comment to a toxic comment with very low confidence score. Moreover, it perturbs too many words and produces grammatically incorrect sentence. For example, easy is converted to slowly. However, slowly does not fit the context and it should not start with an because it does not start with a vowel. Another limitation of the prior work is knowledge transferability. That is, transformations learned in transforming one example to adversarial example is not transferred to other examples or corpus-wide. For example, we saw that in a subset of a dataset, the word examples containing the word best can be converted to adversarial example by replacing best with double T for model by LSTM. This means that there is a correlationship between different examples in the corpus and the knowledge gained by transforming one example to adversarial example can be transferred to other examples. Similarly, another problem with the state-of-the-art work is that they are more focused on classical text classification dataset. However, noisy dataset transformation is not considered by most of the work. Another problem with the state-of-the-art work is the word replacement strategy. Most of the works are focused on single word replacement strategy that has two problems. If a single character level perturbation is used, that is used in deep word bug, that is the state-of-the-art attack, a lot of misspelled words are produced. For example, in this example, it can be seen that the adversarial example generated by deep word bug produces a lot of spelling errors which can be perceived by the user. Similarly, synonym substitution solely produce unnatural examples. For example, replacing fantastic associates outstanding individuals with substituous associate are unresolved individuals are grammatically incorrect. Similarly, placing so with instead in this sentence is grammatically incorrect. Now, as we have discussed the motivation behind our work, I would like to discuss the problem addressed by our work. We wanted to simulate a non-target black box evasion attack against a pre-trained model F such that our attack learns a policy to produce utility-preserving adversarial examples. The policy should learn multi-level transformations and the policy should be transferable to other unseen corpus. We now discuss the framework of ReinforceBug. It can be seen that we have two major components, agent and environment. The agent is responsible for taking an optimal action on the environment state ST such that the optimal action results in adversarial examples. The major modules of the environment are word selector, actuator, and reward generator that will be discussed in the next slide. So the overall process is the agent observes the state and performs an action against the state. The environment has two internal states, that is corpus state and score state. The corpus state is the state of the examples at time t, and the score state is the confidence of target model on the original output of the examples at time t. The actuator performs the action on the state and transforms the original examples in the corpus to candidate examples. The candidate examples are then queried to the target model to obtain the scores. The reward generator then either generates an adversarial example and produces a reward against the transformation selected by the action. The actuator then updates all the state and returns an experience tuple to the model. The model updates its weights and also the action space and then learns to produce another action using the knowledge gained by the previous experience. We now discuss the major modules of the environment component, the word selector. The word selector computes a cumulative score of the importance of word ID X in all the examples in the corpus by removing the word from the original examples and calculating the difference between the score divided by the overall example containing the word. The actuator performs an action. The action is a tuple of three things: the word to be replaced, the action or operation to be performed, and the replication index. The following operations are considered in this work. Each operation results in multiple replacement options. The replacement to be taken against this word is selected by the replacement index. The word reward generator module is the most important module. The reward is calculated in two ways. If the score is less than a threshold, that is, an adversarial example is produced, then the adversarial example gets a reward equivalent to the change in the score plus the semantic similarity divided by the lexical errors, spelling and grammatical errors, and perturbation rate. Otherwise, the reward is equivalent to the change in the score before and after performing the action. Consider the following experimental setup. We have considered three noisy datasets, iron, Twitter, and toxic. How much noisy they are, it can be seen by the average spelling errors and grammatical errors in these datasets. We considered multiple state-of-the-art models. We didn't consider BERT model due to the low performance on the noisy dataset. These are some examples generated by our attack. As you can see, that the models return the misclassification output with a high confidence and also only few grammatical and spelling errors. The result of our attack evaluation is shown in this slide. As you can see, we evaluated our attack on these evaluation matrices, and in most of the cases, our attack outperformed better than TextBugger and TextFooler attack. We also studied the attack transferability on the test dataset, and we evaluated based on the testing time, success, perturbation rate, and lexical errors and confidence score. It can be seen that for most of the matrices, our attack performed better than the state-of-the-art attack TextBugger and TextFooler. We also studied the transferability of our attack on other models. It can be seen that our model resulted in more transferable examples than the other two attacks. We also analyzed the most dreadful operations that are significantly vulnerable for all the text classification model we considered. So we found out that augmenting a semantically similar word with the original important word can significantly change the output of the model. Similarly, we found out that synonym substitution also perform well when generating adversarial examples. The key takeaway of our work is that the ReinforceBug can be used to generate adversarial examples against any model, and it can be used as a tool to find the vulnerabilities in the current deep learning models. Also, it can be used to test their vulnerabilities and also to make them more resilient against adversarial attacks. The corpus-specific policy learned is transferable on other datasets and is partially transferable to other models. Semantic-related and synonym substitution attack pose the highest threat to consider text classification systems. These are some future directions that we are considering: systematic evaluation of vulnerabilities in deep learning models using reinforcement bug, defense against word-level attacks, and conceptualizing a framework towards secure deep learning-based text classification models. That's all from my side. Thank you for listening.